In this video, we'll continue our discussion of Green's theorem by working another example. So we have the line integral over the vector field, and remember our vector field is, there's our mn, and our vector field is defined by the vector mn. So those are parts of my vector field. They define C for me. They said from 1, 0 to -1 along the circle, so you see the top semicircle there. And then from -1, 0 to 1, 0. This is kind of ambiguous now that I'm looking at it. We should say like along the top side of, right? Because I could have went down like that as well. So I won't make test questions ambiguous like that. But we're going through the top. I drew my picture here, again, from like the past reasons. These are x, y. Past reasons being I obsess and want to make it look pretty. So we need to consider C. What we're trying to do here is use Green's theorem. So is it simple? Well, simple means it just doesn't overlap. Yep, we're good. Closed, does it start and stop at the same point? Yes, okay, cool, we're good. And then the region R, is it connected? All right, that means I can take 2 points inside of R, any 2 points, and I can connect them and stay inside of R. Yep. Simply connected means that if I put any open region inside of R, I can contract it down to a point in R. Yeah, that's obvious there. All right, so this means I can use Green's theorem. All right, Green's theorem requires the partial of n with respect to x, and then the partial of m with respect to y, and we'll subtract those two. All right, so n with respect to x is a 0. M with respect to y is also 0. Oh, that tells me the vector field is conservative. Well, I don't need to work this out. I'm going to write this out, but we already know that any work on a closed boundary, that means work is 0. We're done, right? That's the path that we just try to find, or the line integral was representing work. But if it's conservative and it's closed, right, it gets me its path independence. Now, I want to show you how this works out in the theorem, in case you just were like, oh, I'm just going to keep working. It still works out for us. Okay, minus y dy. This is the same thing as the double integral over region R over 0 dA. I don't even need to switch that. We can see that that is 0. So the work, and this lines up with path independence. Path independence tells me that the work is 0 because it's going from this path from here around is the same thing as standing there work-wise. Okay, so you can save some time. You don't even need to do this once you show that it's conservative. If it's conservative and it starts and ends at the same spot, you can just put work is 0. No work is required. I would put maybe like path independence if I was on a test and I wanted to make sure that my professor knew exactly what I knew. So I put maybe F is conservative, work equals 0, path independence. Something like that. But you don't need to do the whole theorem like we did at the bottom. Still not a lot of work. But yeah, conservativeness brings nice calculations.